November 4, 1941. A Tuesday afternoon in Washington, 328 feet of impossibility was about to be sketched on the back of an envelope. The British Admiralty had just sent an urgent dispatch that most naval architects looked at and laughed. They wanted a ship that could cross the Atlantic Ocean in winter storms, then deliberately run itself aground on a hostile beach, unload 20 Sherman tanks in under an hour, pull itself back into deep water, and do it all over again the next day. Oh, and one more thing. They needed 200 of them. Immediately. Captain Edward Cochrane handed the dispatch to John Niedermair, the technical director of preliminary ship design at the Bureau of Ships. Niedermair was 48 years old, not 58 as some records would later claim. Born in Union Hill, New Jersey in 1893, he'd graduated at the top of his class from the Webb Institute of Naval Architecture in 1918. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Since joining the Bureau of Ships in 1928, he'd become the highest-ranking civilian in the organization, responsible for basic designs that would eventually encompass more than 8,000 ships. But on this particular Tuesday, he faced a problem that seemed to violate every principle he'd spent 3 decades learning. The British wanted the impossible. Not difficult, not challenging, actually impossible, according to established naval architecture. Niedermair was a chain smoker who survived on 4 hours of sleep per night. His colleagues described him as obsessive, the kind of engineer who would search a technical problem to its absolute limit, refusing to accept that something couldn't be done until he'd exhausted every possibility. He read the requirements twice, pulled an envelope from his pocket, and started sketching. Not careful technical drawings, rough concepts, working through the fundamental contradictions in real time. The problem was elegant in its simplicity and brutal in its implications. Ships need draft, the depth of hull below the waterline, for stability in rough seas. The deeper the draft, the more stable the vessel. A cargo ship crossing the Atlantic might have a 20-foot draft. Even destroyers, which needed speed and maneuverability, sat 12 to 14 feet deep in the water. That depth prevented them from capsizing when 30-foot waves hit broadside. But beaches don't accommodate deep-draft vessels. Most Pacific coral atolls had reefs extending hundreds of yards offshore in water 3 to 6 feet deep. European beaches varied, but the tidal ranges and gradual slopes meant you needed extremely shallow draft to get close enough to unload. The British requirement specified 3 feet forward draft when beaching. 3 feet. That was barely enough to float a loaded barge, let alone an ocean-going vessel capable of carrying 500 tons of tanks. Every naval architect knew the trade-off. You could build a deep-draft ship for ocean crossings, or a shallow-draft craft for beaching, but not both. The physics simply didn't work. A shallow-draft vessel would roll violently in open ocean, probably capsize in a storm. A deep-draft ship would ground out hundreds of yards from shore, useless for amphibious operations. Niedermair kept sketching. By midnight, he had the basic concept. By dawn, he'd worked out the solution that everyone else had missed. Within 48 hours, the rough sketch was on a ship to England. The British Admiralty looked at it, ran some quick calculations, and immediately wired back a single word. Build. His secret came from submarines. Not an obvious source of inspiration for a surface ship, but Niedermair had spent years working on submarine salvage operations. In 1926, he'd helped raise the S-51 from the ocean floor after it sank in a collision. In 1928, he'd done the same for the S-4. Those operations taught him more about underwater structure, buoyancy, and ballast systems than most naval architects would learn in a lifetime. Submarines dive by flooding ballast tanks with seawater. The added weight makes them heavier than the water they displace, and they sink. They surface by blowing compressed air into those tanks, forcing the water out. The air-filled tanks make the submarine lighter than the surrounding water, and it rises. Simple physics, complex engineering. Niedermair realized he could use the same principle in reverse for a surface ship. The landing ship tank, as it would be designated, would carry enormous ballast tanks running the length of both sides. These weren't small trim tanks for minor adjustments. They were massive chambers capable of holding over 1,000 tons of seawater. At sea, pumps would flood these tanks completely. The ship would settle deep in the water, draft increasing from 3 feet to 14 feet. That depth would provide stability in rough weather. Atlantic storms that would capsize a shallow draft barge wouldn't even faze a vessel sitting that deep. But when approaching a hostile beach, 30 minutes before landing, the crew would activate the ballast pumps. Diesel-powered pumps capable of moving hundreds of gallons per minute. The seawater would be expelled overboard. The ship would literally ride up in the water, and within half an hour, the forward draft would drop to 3 feet 9 inches, shallow enough to reach almost any beach on Earth. The mathematics were elegant, but the engineering was brutal. A fully loaded LST would displace roughly 4,000 tons. To change draft by 11 feet required moving approximately 1,000 tons of seawater in and out of the ballast system. The pumps had to be reliable, the tank structure had to withstand the stress of repeated flooding and emptying, and the hull had to handle the transition without breaking apart. That last part was the real challenge. When you flood ballast tanks on one side of a ship faster than the Basopil, even by a few seconds, you create enormous sideways stress on the hull. When you pump them out, the ship rises unevenly. The forces involved could twist a conventional hull like wringing out a wet towel. Most ships would simply break in half. Niedermair solved this with reinforced longitudinal bulkheads. Think of them as internal walls running the entire length of the ship, made of thick steel plate, connecting the port and starboard sides. These bulkheads would distribute stress across the entire structure. When the ballast tanks flooded unevenly, the bulkheads would prevent the hull from twisting. The ship would flex slightly, which was good. Rigid structures break, but it wouldn't twist catastrophically. Then came the bottom. Traditional ships have a keel, a long structural beam running down the center of the bottom from bow to stern. The keel provides structural rigidity and helps the ship track straight through water, but a keel also means the ship has a V-shaped or rounded bottom. When you beach a keeled vessel, it rolls to one side, completely useless for unloading vehicles. Niedermair gave his design a flat bottom, perfectly flat, like a barge, except 300 feet long and 50 feet wide. When this ship grounded on a beach, it would sit perfectly upright. Tanks could drive off without tilting sideways. Troops could disembark without walking on a sloped deck. The flat bottom created its own problems. Ships with flat bottoms rolled terribly in even moderate seas. The phenomenon is well documented. Without a deep keel cutting through water and providing stability, the ship becomes a cork in a bathtub. Every wave hits the flat bottom and lifts it. The result is a rolling motion that makes everyone aboard violently seasick. Niedermair accepted this. The ship would be uncomfortable. Crews would hate it, but it would work. Sometimes function trumps comfort, and this was one of those times. The propulsion system needed special protection. 2 propellers, one on each side, powered by diesel engines. But propellers are vulnerable. They stick down below the hull, and when you deliberately beach a ship, those propellers would hit sand, coral, or rocks. A damaged propeller means a disabled ship. The solution was recessed propeller tunnels. Instead of hanging the propellers below the hull, Niedermair designed indented channels that protected them. The flat bottom extended beyond the propellers, so when the ship grounded, the props stayed clear of the bottom. Same principle for the rudders. Protected recesses kept them from shattering on impact. And then came the bow. This is where Niedermair completely abandoned conventional ship design. Traditional ships have pointed bows. The physics are straightforward. A pointed bow cuts through water efficiently, reducing drag, allowing higher speeds with less engine power. Every cargo ship, every warship, every vessel designed for efficient ocean travel had a pointed bow. It was fundamental. Niedermair designed a bow that looked like someone had taken a sledgehammer to a normal ship. Flat, blunt, high, rising vertically from the waterline. It looked ridiculous. It looked wrong. Naval architects who saw the early sketches assumed it was a placeholder, that the real bow design would come later, but that blunt bow was the entire point. behind massive clamshell doors that could swing open, behind a steel ramp that could drop down, that flat bow became a loading dock. The doors opened. The ramp, made of quarter-inch steel plate reinforced with heavy I-beams, dropped and extended forward. A 30-ton Sherman tank could drive down that ramp at full speed without the ramp flexing more than half an inch. The bow ramp needed to support not just static weight but dynamic loads. A tank accelerating from 0 to 15 miles per hour while driving down the ramp created impact forces far exceeding its resting weight. The ramp had to absorb that punishment repeatedly, in salt water, without corroding or failing. Hydraulic cylinders provided the main lifting force. 2 massive cylinders, each capable of lifting several tons, connected to the ramp through steel cables and pulleys. When the hydraulics activated, the ramp lifted smoothly. When they released pressure, it dropped. The system was designed with redundancy. If the hydraulics failed, manual chains provided backup. 2 men cranking handles could lower or raise the ramp. It would take longer, maybe 18 seconds instead of 6, but it would work. The initial design called for a ship 280 feet long. That's the length of a modern football field, including one end zone, big enough to carry a reasonable amount of cargo, small enough to build quickly. But in January 1942, as detailed planning progressed, Niedermair and his team realized 280 feet wasn't enough. They needed more tank capacity. The original spec called for carrying 18 medium tanks. Combat commanders wanted 20. That required more deck space. They needed accommodation for up to 160 troops in addition to the tanks. That required berthing space. They needed fuel capacity for a transatlantic crossing, approximately 10,000 nautical miles. That required larger fuel tanks. The design stretched, first to 290 feet. Then, as the final plans went to the contracting firm of Gibbs & Cox for detailed development, to 328 feet with a 50-foot beam. The ship was getting bigger, heavier, more complex. But the fundamental concept remained. Gibbs & Cox took Niedermair's preliminary design and turned it into construction plans that shipyards could actually use. This process normally takes 2 years. Every system needs detailed drawings, electrical layouts, plumbing diagrams, structural specifications, material lists. For a conventional cargo ship, the detailed plans might fill 20 large binders. They had weeks, not years. The British were desperate. German U-boats were sinking cargo ships faster than they could be replaced. The Soviets were begging for supplies. The entire Allied strategy depended on being able to move massive amounts of equipment across oceans and then onto hostile shores. Without these ships, amphibious warfare on the scale required to win the war wasn't possible. Gibbs & Cox worked around the clock. Engineers slept at their drafting tables. The usual review processes were compressed or skipped entirely. By February 1942, barely 3 months after Niedermair's envelope sketch, detailed construction plans were complete and being distributed to shipyards. The first keel was laid at Newport News, Virginia on June 10, 1942, 7 months from concept to construction start. In peacetime, that timeline would be impossible. In war, it was merely desperate. The ship that emerged from the building ways was ugly. There's no polite way to describe it. The blunt bow looked unfinished. The flat sides and bottom gave it a boxy, utilitarian appearance. Compared to the sleek lines of destroyers or the imposing bulk of battleships, the LST looked like a floating warehouse, which is essentially what it was. By October 1942, LST-1 was sliding down the building ways at Newport News. The christening was subdued. No champagne bottles, no elaborate ceremonies. The Navy needed ships, not parties. Within weeks, LST-1 was commissioned and heading for combat trials. But one shipyard, even a major facility like Newport News, couldn't produce the numbers needed. The Navy's procurement office had calculated requirements based on planned operations in both Europe and the Pacific. They needed over 1,000 LSTs, not eventually, not after the war ended. They needed them within the next 2 to 3 years. Traditional shipyards on the coasts were already maxed out. They were building destroyers, cruisers, aircraft carriers, submarines, liberty ships, and dozens of other vessel types. There simply wasn't capacity for a massive LST construction program. The coastal yards were working triple shifts, launching ships as fast as they could lay keels. So the Navy did something unprecedented in American shipbuilding history. They built shipyards inland, along rivers, in places that had never produced ocean-going vessels. Pittsburgh, Pennsylvania. On Naval Island in the Ohio River, Dravo Corporation had been building river barges and bridge components for decades. They knew steel fabrication, they understood welding, they had the industrial base. The Navy awarded them a contract to build LSTs, not one or two prototype vessels. 145 ships. Evansville, Indiana. The Missouri Valley Bridge and Iron Company operated in this Ohio River town, building bridge sections and industrial equipment. The Navy built them a 45-acre shipyard from scratch, starting in March 1942. By June, they were laying keels, even as construction continued around them. Over the next 3 years, they would produce 167 LSTs, more than any other yard in the country. The Chicago Bridge and Iron Company received a similar contract for their facility in Seneca, Illinois, on the Illinois River. Jeffersonville Boat and Machine Company in Jeffersonville, Indiana, got another. American Bridge Company in Ambridge, Pennsylvania, another major facility. These inland yards became known as the Cornfield Navy, a nickname that was both accurate and misleading. Yes, they were building ocean-going ships in the middle of farm country. But these weren't amateur operations. These companies knew heavy steel construction. They understood large-scale fabrication. They just hadn't built ships before. The logistics were absurd. Each LST required 1,200 tons of steel plate. That steel came from mills in Pittsburgh and Gary, Indiana, delivered by rail and barge. The twin diesel engines, each weighing several tons, came from Detroit. General Motors' 12 to 567 diesel engines, the same type used in locomotives, modified for marine use. They arrived by rail, were craned onto barges, and floated to the shipyards. Hydraulic systems came from specialized manufacturers. Electrical components, navigation equipment, weapons systems, all had to be sourced and delivered. The supply chain stretched across the entire industrial Midwest, coordinated by the Navy's Material Coordinating Agency, which was essentially doing real-time, just-in-time manufacturing 40 years before that became standard practice. The yards built the ships in sections, not whole hulls at once. Sections. The bow was fabricated in one area, the stern in another, the midship sections in a third. Each section was essentially a large steel box, assembled from plates that were cut to size, positioned precisely, and welded together. The welding was critical. Riveted construction, traditional for shipbuilding, was too slow. Welding was faster, lighter, and just as strong if done correctly. The problem was finding enough skilled welders. At Dravo's peak operations, they employed 16,000 workers. Evansville employed 19,000. Most had never welded before the war started. Training programs were compressed from months to weeks. Women were recruited heavily, partly because of manpower shortages, but also because supervisors discovered women often made excellent welders. They had steady hands, attention to detail, and the patience for repetitive precision work. By 1943, all-female welding crews were common at both Dravo and American Bridge. The work was grueling. Welders worked inside confined steel spaces, breathing fumes, dealing with temperatures over 100 degrees in summer. The yards operated 3 shifts, 24 hours a day, 7 days a week. Christmas was the only day off. Some workers literally lived at the yards, sleeping in barracks between shifts. Quality control was stringent, despite the pace. Navy inspectors examined every hull seam. Critical welds were X-rayed for hidden flaws. Hull sections were pressure tested. Any defect meant rework, and rework meant delays, and delays meant soldiers dying because equipment didn't arrive. Production time dropped dramatically as workers gained experience. The first LST at Dravo took nearly 6 months from keel laying to launch. By mid-1943, they were producing 1 LST every 6 days. By 1944, 1 every 3.5 days. At Evansville, Peak production hit one ship every 4 days. Think about that. A 328-foot ocean-going vessel, from first steel plate to launching, in 96 hours. The construction process had been so streamlined, so optimized, that it resembled an assembly line more than traditional shipbuilding. The launching ceremonies became major local events. Thousands of people would line the riverbanks to watch. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. When an LST launched sideways into the Ohio or Illinois River, the wave it created could be 6 feet high. Spectators learned to stay well back from the waterline or risk getting drenched. Local newspapers covered every launch. Radio stations broadcast live. These ugly, blunt-bowed ships became a source of civic pride. The ships themselves were numbered, not named. LST-1, LST-2, LST-3, 8, 6, LST-5, 4, 2, LST-7, 8, 9. The Navy didn't bother with traditional naming ceremonies because they were building them too fast. Names would come later, if at all. Many served their entire combat careers identified only by number. Once launched, the ships weren't finished. They floated to fitting out docks where engines were installed, electrical systems connected, weapons mounted. Then came trials. Each ship had to prove it could steam, maneuver, and handle basic operations before the Navy would accept it. After acceptance, the LSTs faced their longest and strangest voyage. They had to get from the middle of America to the ocean. From Pittsburgh or Evansville or Seneca, they sailed down the Ohio to the Mississippi, then down the Mississippi to New Orleans, a journey of hundreds of miles through locks, past river traffic, navigating currents and sandbars. The crews were often assigned before the ships even reached salt water. 90 to 120 officers and enlisted men, most barely out of training, would report aboard in New Orleans. Many had never seen the ocean. Farm boys from Indiana found themselves commanding 300-foot warships. The training was compressed, basics taught on the move. From New Orleans, the LSTs sailed into the Gulf of Mexico. For many crews, this was their first experience with the ship's notorious rolling characteristics. In the relatively calm Gulf, the flat-bottomed design would roll 15 to 20 degrees in any moderate swell. Seasickness was universal. Crew members who'd never been on a boat before were suddenly dealing with waves, pitching decks, and the overwhelming nausea that comes from constant motion. The nickname large slow targets emerged early. LSTs were designed for 10 to 12 knots maximum speed. In practice, fully loaded, they averaged 9 knots. That's about 10 miles per hour. A person can jog faster than an LST could sail. In a world of destroyers capable of 35 knots and submarines that could submerge to escape, the LSTs were sitting ducks if caught in combat without escorts. But the nickname, while accurate, missed the point. They weren't designed to fight. They were designed to deliver. Speed didn't matter if you could beach anywhere, unload directly onto sand, and have tanks rolling inland within minutes. Those capabilities remained theoretical until they were tested in combat, and that test was coming. In June 1943, 73 LSTs sat offshore from Guadalcanal, loaded and ready. Niedermair's envelope sketch was about to face Japanese defenders, coral reefs, and tropical beaches. Either the design would work, or thousands of Marines would discover their primary logistics support was fatally flawed. The moment of truth was approaching. June 30th, 1943, 73 LSTs sat offshore from Lunga Point, Guadalcanal, engines idling, bow doors sealed, loaded with 12,000 Marines and enough heavy equipment to support an entire division. This was Operation Toenails, the push north through the Solomon Islands, and it represented the first major combat deployment of American-built LST-2 seconds in the Pacific War. The beach at Lunga Point wasn't heavily defended. Japanese forces had largely withdrawn inland, focusing on maintaining control of the jungle interior rather than contesting every shoreline. This was fortunate because it meant the LSTs could test their systems without the immediate pressure of heavy fire. At 0700, the first wave approached the beach. Coxswains in the control stations navigated by eye, watching the shoreline, judging distances, calculating the approach. There were no sophisticated navigation aids, no radar to measure depth, just experience, instinct, and orders to beach at full speed. The first LST hit the beach at 9 knots, its blunt bow riding up onto volcanic sand. The grinding sound of the hull on sand was loud enough to hear on the transports offshore. Inside, Marines braced themselves for the impact. But there was no crash, no violent stop. The ship slowed gradually, momentum bleeding off as friction increased, until it settled with barely a shudder. The ballast pumps had been running for 30 minutes, emptying the side tanks. The ship sat high in the water, draft reduced to the minimum. When it grounded, the forward section was in less than 4 feet of water. The bow doors swung open with a hydraulic hiss. The ramp dropped. Steel clanging on steel, then the thud as it hit sand. The entire process, from grounding to ramp down, took 45 seconds. Sherman tanks rolled off, one after another. The first tank hit the ramp at maybe 5 miles per hour. Cautious, the driver not sure if the ramp would hold. It did, barely flexed. He accelerated, hitting the sand, tracks churning. 29 tons of steel and armor rolling directly from ship to shore without touching water. The second tank followed 15 seconds later. Then the third. The fourth. A steady mechanical procession. Each tank drove off, moved 50 yards inland to clear the beach, and the next one started down. 4 minutes per vehicle, including the pause between. 5 tanks, 20 minutes. Then came the jeeps, the trucks, the towed artillery pieces. What shocked the Marine officers coordinating the landing wasn't the speed, though that was impressive. It was the volume. A single LST carried 20 tanks, 30 vehicles, and provisions for days of operations. When that LST unloaded in 30 minutes, reversed off the beach, and headed back for a second load, the Marines realized they were watching logistics warfare at a scale they'd never imagined. By noon, the beach was overwhelmed with supplies, not because the landing was going poorly, but because it was going too well. LSTs were delivering cargo faster than the Marines could move it inland. Mountains of ammunition crates, fuel drums, ration boxes, all piling up in the tropical sun. Bulldozers couldn't keep up. Storage areas filled beyond capacity. The beachmaster, a Navy lieutenant whose entire job was coordinating traffic flow, radioed the flagship with a message that would have been incomprehensible in any previous war. Request slow down LST arrivals. Beach capacity exceeded. Think about that. In the history of amphibious warfare, stretching back thousands of years, no one had ever asked an invasion fleet to slow down because supplies were arriving too fast. The bottleneck wasn't delivery, it was distribution. Getting equipment from ship to shore was solved. Getting it from shore to frontline units remained a problem, but that was an Army, logistics issue, not a Navy one. The Navy adjusted. Instead of continuous arrivals, they spaced LST landings at 15-minute intervals. This gave ground crews time to clear each load before the next ship beached. The system worked so smoothly, it became the template for every subsequent operation in the Pacific. Over the next 6 months, LSTs demonstrated capabilities even their proponents hadn't fully anticipated. At Tarawa in November 1943, they saved the entire operation from potential disaster. Tarawa was supposed to be a quick operation. Naval bombardment would pulverize the defenses, and Marines would land in Higgins boats, secure the beach in a day, maybe 2. The plan fell apart within the first hour. The coral reef surrounding Betio Island extended 500 yards from shore. Intelligence had predicted the tide would be high enough for Higgins boats to float over the reef. Intelligence was wrong. The tide was 18 inches lower than expected. Higgins boats grounded on coral 500 yards from shore. Marines had to climb out and wade through chest-deep water under machine gun fire. They were slaughtered. Bodies floated in the lagoon. Boats full of wounded couldn't get back out through the reef. LSTs, drawing only 3 to 4 feet of draft fully loaded, rode right over that reef like it wasn't there. The coral scraped along the bottom with a sound like grinding teeth, but the hulls held. They grounded within 30 yards of shore, close enough that their ramps reached dry sand. The Marines who'd been pinned down in the water suddenly had a covered approach. They could wade to the LSTs, which became floating cover points, then move up the beach using the ship's bulk for protection. It wasn't elegant, it wasn't what the LSTs were designed for, but it worked. Then came the second unexpected benefit. After delivering their initial loads of tanks and equipment, the LSTs became casualty evacuation ships. The tank deck, normally packed with vehicles, could hold 200 stretcher patients. Corpsmen set up triage areas on the main deck. Doctors performed emergency surgery on folding tables surrounded by steel walls. It was crude, cramped, and impossible to sterilize properly, but it was medical care within minutes instead of hours. At Tarawa, LSTs evacuated over 900 casualties over 3 days of fighting. Men who would have died waiting for hospital ships survived because they got blood transfusions and emergency surgery aboard LSTs. The ships weren't equipped as hospital vessels. They had no operating theatres, no recovery wards. But they had space, they had basic medical supplies, and most critically, they could get to the beach and back quickly. The pattern repeated across the Pacific: Bougainville, Markin, Kwajalein, Eniwetok. Each invasion relied on LSTs as the primary heavy equipment delivery system. The ships took punishment that amazed engineers back home. At Bougainville, LST 449 hit a coral head that punched through the hull, plating forward, flooding the front ballast tanks. The crew couldn't pump them out completely. The ship sat low in the water, sluggish, bow heavy. They jury-rigged additional pumps, patched the hole with concrete and steel plates welded over the damaged area, and the ship completed 3 more landing operations before heading to a repair facility. At Saipan, LST 341 grounded on volcanic rock with such force that 30 feet of bottom plating was scraped away, exposing the internal structure. The ship leaked continuously. Pumps ran non-stop to keep ahead of the water. But the hull didn't split open, the structural bulkheads held, and LST 341 completed its mission before limping to dry dock. Navy engineers had predicted LSTs could survive maybe 10 combat landings before accumulated stress damage rendered them unusable. The repeated grounding, the constant flexing of the hull, the shock loads from hitting beaches at speed, all of this should have created cumulative fatigue failures. The reality exceeded predictions dramatically. Some ships made 30 landings, some made 50. LST 393 participated in 38 different beach operations between November 1943 and April 1945. The hull was battered, paint worn away in places exposing bare steel. The ballast system needed constant maintenance, but it kept operating. Part of this durability came from Niedermair's conservative design approach. He'd overbuilt everything. The longitudinal bulkheads were thicker than strictly necessary. The bottom plating was heavier gauge steel than calculations suggested. This added weight, reduced speed, cost more to produce, but it meant the ships could absorb battle damage and keep functioning. Then came Europe. June 6, 1944. The invasion of Normandy required logistical support on a scale never attempted in warfare. 156,000 troops landing on 5 beaches simultaneously, backed by thousands of vehicles, artillery pieces, and supplies for sustained operations inland. Without ports, without piers, direct from ship to shore, LSTs were the backbone of this logistical miracle. Over 150 participated in the initial assault waves. They'd been loading for weeks in English ports, stacking vehicles so precisely that there was barely an inch of clearance. Every square foot of deck space utilized, every pound of cargo calculated. At Utah Beach, conditions were nearly ideal. The beach gradient was gentle, about 1 in 50, exactly what the LSTs were designed for. Tidal range was manageable. German resistance, while significant, was lighter than planners had feared. LSTs began arriving at 0630, just behind the first infantry waves. The sight must have been surreal for German defenders who survived the initial bombardment. Massive grey ships charging directly at the beach, not slowing, not turning, deliberately ramming themselves onto French soil. The bow doors opening like giant mouths, tanks driving out as if the ships were mobile garages. By 0900, tank companies were rolling inland from Utah Beach. The first LSTs were already reversing off, backing into deep water, turning for the trip back to England to collect second loads. The operation ran so smoothly that some LSTs made return trips to England and were back at Utah Beach with fresh loads by late afternoon. Omaha was different. Everything that could go wrong did. The beach was steeper, heavily fortified, and defenders had pre-sighted every approach. When LSTs started arriving at 0800, they found themselves approaching a killing field. Bodies floated in the surf, burning landing craft, American forces pinned behind a seawall, unable to advance, taking heavy casualties. The LST commanders faced an impossible choice: beach according to schedule and risk getting blown apart, or hold offshore and wait for the beach to be secured, abandoning the men already ashore. They beached LST-47, grounded at 0915 under direct fire from an 88mm gun positioned in a concrete bunker overlooking the beach. The gun crew had the range perfectly. The first shot missed, hitting water 20 yards short. The LST's bow doors were already opening. The second shot hit the bow ramp just as it started to drop, punching through steel plate, sending shrapnel into the tank deck. A Sherman tank rolled down the damaged ramp anyway. The tank commander had his turret open, standing half exposed to direct the driver. He spotted the German gun position, traversed the turret while still on the ramp, and fired. The 90mm tank round hit the bunker's firing slit. Direct hit. The German gun fell silent. The Sherman continued onto the beach, engaged 2 more positions, was hit by return fire and disabled, but the crew survived. Behind it, the rest of LST-47's cargo rolled off. The ship took 2 more artillery hits while unloading, but completed the operation and withdrew. 7 crew members wounded, none killed. The ship itself remained operational. This scene repeated across Omaha Beach. LSTs arriving under fire, taking hits, unloading anyway, withdrawing damaged but functional. By noon, 29 LSTs had beached at Omaha despite German artillery. 5 were seriously damaged. 2 took direct hits that killed crew members. But 27 successfully unloaded and withdrew. The supplies kept flowing. The psychological impact on German defenders was devastating. They'd been told the Allies couldn't sustain a major invasion without capturing ports first. Watching endless waves of ships deliberately beach themselves, disgorge tanks, and continue operating shattered that assumption. The Allies weren't just attacking, they were establishing permanent logistics infrastructure in real time, directly onto hostile shores. By the end of D-Day, LSTs had delivered over 3,000 vehicles to Normandy beaches, 9,000 tons of supplies. These numbers only increased in the following days. When a massive storm destroyed the Mulberry Artificial Harbour 2 weeks later, LSTs became the primary resupply method. They continued operations throughout June and into July, landing cargo directly onto beaches while engineers worked to open the port of Cherbourg. The cost was real. 26 LSTs were lost during the entire Normandy campaign, most to mines or underwater obstacles. German engineers had planted thousands of steel stakes, concrete pyramids called tetrahedrons, and saw-blade obstacles below the high tide line. These were designed specifically to rip open hulls. LSTs learned to time landings for high tide, floating over the obstacles, then settling onto sand as the tide receded. Back in the Pacific, the island-hopping campaign had evolved into an LST-dependent operation. MacArthur's forces couldn't have pushed from New Guinea to the Philippines without them. Nimitz's drive through the Central Pacific, from the Gilberts to the Marshalls to the Marianas, was essentially an LST convoy system spanning 5,000 miles. The invasion of Leyte Gulf in October 1944 demonstrated the evolved doctrine. Over 100 LSTs participated in the initial landings on October 20th. They delivered 200,000 tons of equipment in the first week. Ammunition, fuel, construction materials, medical supplies, food, everything an army needed to fight and survive. MacArthur waded ashore at Leyte with photographers capturing the moment, fulfilling his promise to return to the Philippines. Behind him in the photographs, barely visible but critically important, were the blunt bows of LSTs. Those ships had been concepts on an envelope when he'd left the Philippines in 1942. Now, they were delivering his army back, but Leyte also revealed a terrifying new threat. November 12, 1944, a day LST sailors would remember as Bloody Sunday. Kamikaze pilots appeared over Leyte Gulf shortly after 0800. Not bombing runs or strafing attacks, suicide dives. Pilots deliberately crashing their aircraft into American ships. The concept was shocking, incomprehensible to Western military doctrine, but it was devastatingly effective. LSTs anchored in Leyte Gulf made perfect targets. Large, slow, unarmored, loaded with fuel and ammunition, a kamikaze hit could create a catastrophic explosion. That morning, Japanese pilots found targets everywhere. LST-738 was unloading when a Zero fighter dove from 3,000 feet. The 20mm gunners opened fire, but the range was too close, the angle too steep. The Zero crashed into the open tank deck, its fuel tanks rupturing, gasoline spraying across stacked ammunition crates. The resulting explosion killed 27 crew members instantly and wounded 49 others. LST-66 was approaching shore when lookouts spotted another kamikaze. The pilot was visible through the cockpit, face determined, aircraft diving at terminal velocity. The gun crews fired continuously. Tracers laced the sky. They hit the Zero repeatedly, shredding wings, puncturing the fuselage, but momentum carried it forward. The plane missed the ship by 30 feet, crashing into the water so close that shrapnel peppered the hull and superstructure. The spray from the impact drenched the deck. LST-460 wasn't as fortunate. A kamikaze penetrated the anti-aircraft fire and struck amidships. The explosion was so violent it broke the ship's back. LST-460 settled in shallow water, a total loss. 13 survivors were rescued by neighboring ships. 47 others died in the impact and fire. That single day, November 12, 1944, saw 8 LSTs damaged or destroyed by kamikaze attacks. But 89 other LSTs completed their landing operations. The Japanese strategy of terror worked on individual ships but couldn't stop the mechanical flow of supplies. For every LST hit, 3 more arrived. The Americans were trading industrial capacity for strategic position, and they had capacity to spare. The kamikaze threat continued through the final months of the war. LST crews developed tactics. They painted additional anti-aircraft guns on the decks. They learned to put up maximum fire at approaching aircraft, creating a wall of tracers that even suicidal pilots struggled to penetrate. They learned to maneuver violently when under attack, using the ship's sluggish handling to best advantage. But there was only so much you could do. Kamikazes were small, fast, and the pilots were committed. Some got through. LST-884 was hit off Mindoro in December. LST-750 off Luzon in January 1945. The casualties mounted, but the operations never stopped. By early 1945, LSTs had become so essential that Pacific operations were planned around them. The invasion of Iwo Jima in February deployed 63 LSTs. The planning documents explicitly stated that without LST support, the operation couldn't be sustained beyond the initial landings. Iwo Jima was 8 square miles of volcanic rock, heavily fortified, defended by 21,000 Japanese troops who'd had months to prepare. The Marines knew it would be brutal. What they didn't know was how brutal. The battle lasted 36 days. American casualties exceeded 6,000 dead and 20,000 wounded. LSTs provided the logistical backbone. They delivered replacement troops, evacuation wounded, brought ammunition forward, and created supply dumps directly on the black sand beaches under Japanese artillery fire. Some LSTs made 15 or 20 trips between ships offshore and the beach, operating continuously under fire. The black volcanic sand created its own problems. It was so fine that vehicles bogged down immediately. Bulldozers sank to their tracks. LSTs had to position themselves perfectly, dropping their ramps on the few patches of firmer ground. When they got it wrong, equipment became stuck on the ramp, blocking everything behind it until it could be winched free, because that's what LSTs did. They were crude, uncomfortable, slow, and ugly. But they worked. Under fire, in bad weather, on terrible beaches, they delivered. Okinawa was worse. The invasion began April 1st, 1945. Over 140 LSTs participated. The battle lasted 83 days, the longest and bloodiest in the Pacific War. Kamikaze attacks were constant. The Japanese flew over 1,500 kamikaze sorties during the Okinawa campaign. LSTs operated in rotation. Land supplies under fire, evacuate casualties, withdraw to relative safety offshore, then return the next day, and the next, and the next. For nearly 3 months, crews worked past exhaustion, functioning on adrenaline and determination. One LST commander described it as industrial warfare at sea. His ship, LST-615, made 17 landings at Okinawa between April 1st and June 20th. Each time, the crew knew kamikazes would come. The ship's gunners shot down 3 confirmed aircraft. The vessel took minor shrapnel damage twice. One landing was delayed when a kamikaze hit an LST 30 yards away, creating a fireball that engulfed both vessels in heat and smoke. They pulled back, waited for the fire to burn out, then completed the landing. The strain on crews was immense. These were 19- and 20-year-old kids, farm boys from Indiana, factory workers from Pennsylvania, clerks from California. They'd received 6 weeks of training, been handed a 300-foot ship, and told to sail it across the Pacific into combat. They lived in cramped quarters that rolled sickeningly in any weather. They worked 18-hour shifts during landing operations. They watched sister ships get blown apart while mechanically continuing their runs. Yet the LSTs kept operating, because Niedermair's design, for all its ungainliness and discomfort, was fundamentally sound. The ballast system worked. The bow ramp mechanism held up under repeated use. The flat bottom took repeated groundings without failing. Most importantly, the ships were simple enough that teenage crews could keep them running with basic maintenance and whatever spare parts they could scrounge. When Japan surrendered in August 1945, over 1,000 LSTs were still operational across the Pacific. They immediately shifted to occupation duty, ferrying troops and equipment to Japanese ports. Several LSTs participated in landing operations at Tokyo Bay, delivering American forces directly onto Japanese soil. The symbolism was potent. 4 years earlier, these ships hadn't existed. Now they were establishing American presence in Japan itself. The war ended, and most wartime vessels became obsolete overnight. Jets were replacing propeller aircraft. Missiles were replacing guns. Aircraft carriers were getting larger, destroyers more and sophisticated. But LSTs kept working. Korea brought them back into combat in 1950. The Incheon landing in September used 47 LSTs executing the same doctrine developed at Guadalcanal: rough beaches, no port facilities, direct delivery of tanks to combat zones. The communist forces defending Incheon had never seen amphibious operations at this scale. The suddenness of having American armor rolling off beaches behind their lines broke their defensive positions. LSTs served through Vietnam. They ran supplies up rivers, delivered equipment to remote bases, evacuated casualties from coastal positions. They operated during the Gulf War. The last LST in active U.S. Navy service, USS Frederick, was decommissioned in 2002, 60 years after the first one launched. Some foreign navies still operate LSTs today: the Philippine Navy, the Indonesian Navy, the Taiwanese Navy. These are descendants of the original 1942 design, updated with modern engines and electronics, but fundamentally unchanged. The basic concept remains valid. If you need to deliver heavy equipment directly onto a beach, the LST design still works. But the real legacy isn't longevity, it's doctrinal. Before LSTs, amphibious warfare required capturing ports. Armies had to seize harbors, clear them of obstacles, repair damage from demolitions, before heavy equipment could land. This process took weeks or months. After LSTs, any beach became a potential invasion site. The Allies could choose where to fight based on strategic considerations, rather than being constrained by port locations. This fundamentally changed military strategy. It made island hopping possible in the Pacific. Without LSTs, American forces would have needed to capture every Japanese-held port, fight for every fortified harbor. The campaign would have lasted years longer. Instead, they could bypass strong points, land on undefended beaches, establish supply bases, and move on. It made Normandy possible in Europe. German planners assumed the Allies would attack a major port, probably Calais or Cherbourg. They fortified those areas heavily. When the Allies landed on open beaches and sustained operations through direct ship-to-shore delivery, German strategy collapsed. It changed the fundamental equation of naval power. Before LSTs, navies existed to control sea lanes and support ground forces from offshore. After LSTs, navies could deliver ground forces anywhere there was coastline. The ocean stopped being a barrier and became a highway. John Niedermair retired from the Bureau of Ships in 1958, having directed basic designs for over 8,000 vessels: battleships, aircraft carriers, cruisers, destroyers, submarines, and those ungainly flat-bottomed landing ships that everyone initially thought looked ridiculous. He received the Navy's Distinguished Civilian Service Award in 1945, the highest honor available to non-uniformed personnel. The American Society of Naval Engineers called him the father of the modern U.S. Navy. He received the David Taylor Gold Medal, the Gibbs Brothers Gold Medal, and recognition from virtually every major engineering society in America. But in a 1978 oral history interview, when asked about the LST, Niedermair remained characteristically modest. "It was just a way to solve a problem that needed solving," he said. "I kept digging at the things I didn't know. I'd search a thing out to the limit." That problem was how to turn the ocean from a barrier into a highway, how to deliver overwhelming force directly onto hostile shores without waiting for ports to be captured and repaired, how to make geography irrelevant to military planning. Niedermair solved it by borrowing ideas from submarines, ignoring every rule about proper ship design, and trusting that crude but functional would beat elegant but useless. His envelope sketch, drawn in 48 sleepless hours in November 1941, created a capability that shaped the entire course of World War II. Dwight Eisenhower understood this better than most. After the war, in conversations with military historians, he named 3 technologies that won the war: the C-47 Dakota transport plane, the Jeep, and the LST. Not battleships, though they provided critical fire support. Not bombers, though strategic bombing crippled German industry. The 3 technologies that enabled Allied forces to fight where they chose, when they chose, with the supplies they needed. The LST was the least glamorous of the 3. No one wrote songs about it. Hollywood never made movies celebrating LST crews. There are no monuments to these ships in major cities. Most Americans couldn't tell you what LST stands for, let alone describe what these ships did. But every Marine who drove a tank off a ramp onto hostile sand, every soldier whose life was saved because medical care arrived within minutes instead of hours, every airfield built with equipment delivered directly to remote beaches, they all benefited from John Niedermair's refusal to accept that something was impossible. He died in March 1982 at age 88, having lived long enough to see his impossible design serve in 4 wars and influence military doctrine for 2 generations. There's no aircraft carrier named after him. No destroyer bears his name. Most Americans have never heard of John Niedermair. But the next time you see footage of any amphibious landing, any operation where ships beach themselves to deliver cargo directly onto shore, you're watching the legacy of one engineer's 48-hour marathon in November 1941. One envelope sketch that proved the experts wrong. The LST didn't win the war alone, but it made winning possible on the terms the Allies chose. It transformed the ocean from an obstacle into an advantage. It gave commanders the freedom to strike anywhere coastline existed. And in a war that spanned 3 oceans and 5 continents, that freedom was everything. Sometimes the most important innovations aren't the ones that look impressive. Sometimes they're the crude, ugly, functional solutions that everyone initially dismisses. The LST was never beautiful. It was never fast. It was never comfortable. But when Marines needed tanks on beaches, when wounded men needed evacuation, when armies needed supplies delivered to places no port existed, the LST was there. Reliable, unglamorous, essential. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.